Line A4, we are dealing with learning task number 8, and this is going to be video 8. Oh, no, I was going to say D, but it's actually 8 Echo, 8E that we have over here, because we are now working into the practical AC circuits, meaning circuits that are going to go and have both my resistance and my inductance inside of the same circuit. Over here, we're given for our first one that has got a practical type of inductance inside of there. I see that, whereas I've got a branch that is made up of both an inductive value and a resistive value, because inductors are made out of copper, right? So we're going to go and analyze, we're going to take down a bunch of values, and then what they're asking us to go and do is to go and find the size of the cap that we would have to place across here to go and drive this thing into resonance. Now here is something we need to be very, very careful about, okay? Huge exclamation point over here. What is resonance? Resonance is when my VARs are going to be equal and opposite. I'm going to cancel out my total amount of power that I'm going to go and have for something. This is very, very important that we go and say that it's going to be the VARs must equal the VARs, not necessarily XL that is going to go and equal my XC, okay? In this case, it's not going to be, because if I were to take a look at this, I should know that there's going to be two things that are going to be completely different. First of all, if I just say that my XL has to equal my XC, I would run into this problem where I'm placing a full value of 120 volts over top of this cap over here. But this one, if I take a look, it's a series circuit, which means that it is going to go and have some sort of a value that is going to go and be less than 120 volts, right? That this thing would have to have over top of it, which means that they would not be apples to apples, right? If I have 120 volts over top of both of these and they both have the same XL, it's going to work out. But if I go and use the same value of opposition, my XL and XC, but I have a lot less, let's say that this thing works out to be like 80 volts or something like that, E squared over R, we see that we would end up at a way different power. We would not get cancellation. So don't get trapped in that thing where you're like, I'm going to go and solve this thing for the XL, so they're going to be the same. If they were truly in parallel with each other, in other words, if I only had, I cannot erase that. If I only had inductance in that branch, then I could go and use it. But because this is now a compound branch, I cannot go and do that XL versus XC. Okay, if you don't get what's going on here, you got to come talk to me later on when we're inside of class. But it's super important that you make this differentiation now before it, leads you down the road to ruin later on. Okay. Let's do the proper solve for this one. They ask us for a bunch of different stuff. They want to go and know our amps inside of each branch. So they want to know that amps. They want to go and know this amps over here. They want to know the watts of this one. They also want to know the watts of this one. They want to know the resistance of this one. They want to know the XL of this one. That's where you're going to get tripped up if you play around with that one afterwards. And then last of all, they want to go and know the total amount of capacitance that I would need to go and match these over here. Let's start with the easy stuff. The easy ones for us to go and deal with is just going to be current. We're going to follow the same format as what they're doing over here, where they're saying, look, we got 120 volts going across from here to here. It's pretty easy for us to establish a value of current, right? If I take I is equal to my E over top of R, 120 volts over top of 40 ohms is going to equal a value of 3 amps. Put that in here, 3 amps for that branch over there. What about for this one over here? Well, it's going to be 120 volts going across from here to here, and I see that I've got a total circuit impedance, a Z, which is the vector sum of these two. I've got a Z of 10, so if it's 120 divided by 10, I know that I'm going to go and have an amps of 12 amps, 120 divided by 10. Lovely. I know that because these two components are in series, all of that 12 amps flows to this inductor, all of that 12 amps flows through this resistor over here. I don't know anything else about this branch yet. We will get to, solving some stuff about this branch, but what we're first going to do is we're going to go back to this value over here. I've got power. For us to go and figure out what we have inside of here, we need to go and figure out how many watts we have inside of here. It's the only other value we can solve for inside of here. And in order to do that, we need to subtract out the watts that are going to be from here, because this watt meter is reading everything inside of our circuit. Let's take that watt meter and let's go and find out how many of those are coming from this section over here. Two different ways we can go and solve for this. We could do E squared over R. That would be 120 squared over top of 40 ohms. That would be good. It's a given value. Or I could go and take my E times my I, 120 volts times 3 amps. So I'm going to do that one. Power is equal to my E times my I. In this case, the type of power we're looking for is watts. So 120 volts times 3 gets me to 360 watts. Stick that over there, 360 watts. Now, if I've got a grand total of 1224 watts, 1, 2, 2, 4 watts, and if I take away 360 watts, remember, watts are those beautiful things where we can just add and subtract them no matter if they're series or parallel. So I'm just going to go and subtract that 360 out of here, which is going to go and leave me with a value of 864 watts over here. Perfect. Once we have got this thing down to that watts, we can now go and figure out the rest of our components that we are going to go and have off of this one. Because as watts, I've got watts and amps, and I know that my power is equal to my I squared R. I do have a value of current over here. That value of current is 12 amps that I've got going through here. I've got a value of power, so I can go and solve for my resistance just by dividing both sides by I squared. So I end up at power over top of I squared is equal to my value of R. So we'll do that. We're going to go take 864 divided by 12 squared. 864 divided by 12 squared, which is going to go and get me to a value of 6 ohms of resistance. 6 ohms of resistance. I do have an impedance already, which is going to be a hypotenuse of the triangle, just the triangle for this little branch over here, but it's still in a hypotenuse, a Z. I've got an R. So what I can do now is I can go and take that as 10, I can take this as 6, and then I can go and figure out what this side is going to be. My gut instinct, it's going to be a 3, 4, 5 triangle, just looking at these two sides over here, but hey, we better double check just to make sure. We're going to go and take 10 squared, right, because we're working with resistance, 10 squared minus 6 squared, and take the square root of that. That's going to be Pythagoras over there, which is then going to go and give us a value for this side over here. Square root of, make sure we throw that bracket in there, 10 squared minus 6 squared, bracket that thing off, equals 8. It is a 3, 4, 5 triangle that we have over here. I drew it wrong. It should be taller like that. Perfect. Okay, so we've got this now as my 8 ohms XL. Here's where you're going to have to be very careful. If you were to go and take this 8 ohms XL, and if you were to try to place a capacitor across here that was going to be 8 ohms as well, we're going to end up with different values. We're going to look at that in a minute. You know, that whole 8 ohms thing and how that would affect our calculations. What we're going to do though right now is we are going to go and create a form of power across here, because we cannot go and figure out the VARs and the microfarad rating of the capacitor until we know what this VARs is going to be. We have to cancel out the VARs. It doesn't matter how we cancel the VARs, as long as we can cancel the VARs, then we would be at resonance. Do I have anything that I can develop power off of? Absolutely. Power is equal to my I squared R. Right? So if I've got a form of power, VARs, it could be equal to my I squared times my XL. So we're going to go and do that. 12 squared multiplied by 8. 12 squared times 8 gets me to a value of 1152 VARs. 1152 VARs. So we're going to need to place a new cap across the circuit over here that is going to go and have the same amount of VARs that we would have. I just want to go and do a bad calculation right now, okay? This is going to be bad calculation. Don't be writing this one down. I'm just going to show you how this thing could get screwed up. If I decide that I'm going to go and use XL as equal to XC, some cases it works in resonance when I've just got those two in parallel, the way we talked about earlier. But in this case, because I got a series circuit here, and I've got this one standing alone, they would not have the same values of voltage. Watch this. If I go and develop my power off of this, E squared over top of R, that's a formula for power. If I take my full source voltage, 120 volts squared, divided by 8, I'm going to end up with a value of 1800 vars. Is 1800 vars equal to 1152 vars? No, absolutely not. It's not. So let's just not do that. Okay, that's a crazy thing. We're going to leave that alone. Instead, we're going to go and cancel out the vars to the vars. Why? Because power doesn't lie. Resistance can lie to us sometimes, right? That's why we like to go and work inside of the power triangle if and when we can. I need to cancel 1152 vars. That's what I'm going to have here, var C, that I'm going to need to place on there. What do I know about this? I don't know a whole lot, but I can work off of those same formulas, and I can form my XL off of that, right? We know that same formula, E squared over top of R equals power. So I could go and cross multiply. Take power down to the bottom, take R up to the top. That forms an R, that forms a P like that. So E squared over top of power is equal to my resistance. In this case, because it's all capacitive, my power type would be vars. My resistance type would be my XC. So we're going to do that. We're going to go and take, let's remove that. We're doing the good thing right now, by the way. I should take 120 squared and divide it by 1152. E squared divided by P, 1152, equals 12.5 ohms. So I need to go and have 12.5 ohms XC. Do note that that is not the same value as my XL. XL and XC, not equal. But the vars are, and that's all that matters. Okay, if I've got this XC, the last thing that I need to do is I know that my XC is equal to 1 over top of 2 pi FC, like that. So I'm just going to cross multiply XC down to the bottom and C up to the top, like that. And then I can go and find my value of capacitance. We'll do that, 2 times pi, so bracket. We're going to start with a bracket because we're going to reinvert the whole thing. 2 pi times my frequency of 60 times my XC of 12.5, bracket, and then we will reinvert, and we get to a value of 0.000212. So this is my millizone, this is my microzone, 212 microfarads that I'm going to go and have. 212 mu F that we are going to need for this one. Perfect. Once again, inside of your binder, they do not seem to be able to go and handle Greek letters very well. Micro, it has been dropped off of that one, so just make sure you throw that one back on. All right, let's move on to the next one that we have over here. This next one that we have over here is a parallel circuit that is going to be what they refer to as an RZ circuit, because they're giving us a impedance for this. Now, there's a couple of things that are really going to shortcut this one for us. Particularly the fact that we've already got a power factor for this thing that we're going to be able to go and utilize. And we're going to go and jump through a couple of just random little, I guess not really random, they're actually quite planned, little steps that are going to allow us to get to our final results really, really quickly. They ask us, calculate the total line current and the power factor for the circuit. Now they're describing, and there's a whole paragraph up ahead of it, they're describing a motor. And motors do have inductance. They're going to go and use coils, and they're going to use those coils as transformers to go and send flux across to the rotor, the rotating part, which is then going to go and generate currents inside there, which then causes magnetic fields, which causes the rotation. It's a lot of jumping together steps, but it's something you're going to learn about when you hit third year. They do have that inductance. They're also going to go and have a lot of resistance inside of it. If you ever put your hand on top of an operating motor, you'll feel that that motor is hot. There is heat that is coming off of it. Thankfully, the bulk of the circuits that we're going to have to solve are going to look very similar to this, where we're going to go and have this power factor that's already going to be given to us. And so we're going to now just go back into some early stuff we covered. We know that power factor was equal to my watts over top of my VA. And if we took a look at that inside of a triangle, we said that my VA was going to be the hypotenuse, my watts was going to go and be this side over here, right, the x-axis, which really means that what we were looking at was a ratio of our adjacent over top of our hypotenuse, which was our cosine. And we've already covered this, that if we go and take the cosine of theta, it equals our power factor. Which means that if we take the inverse cosine of our power factor, it's going to go and equal theta. One converts from one to the next, back and forth like that. Which is awesome, because if we have got power factor, we're almost always given power factor, then that means that we have got a phase angle, and if we've got an impedance, we can go and figure out a total amount of power of VA at a specific phase angle, and then we just add all of these numbers together. This is what we're going to go and do inside of here. Let's start by doing a conversion on this one. This is going to be, once again, a lot different than what's inside of the binder. They're going through this binder, they've got a load of triangles going left, right, and center, and then they're going to go and do a bunch of, trig and fractions and stuff like that, Pythagoras, etc. We're going to shortcut. We really do not need to go through all of that when we've got this calculator that's going to go and take care of it for us. So let's go and take this 60% lagging power factor, and we're going to go and take the inverse cosine of 60%. So second inverse cosine 0.6 gives me a value of 53.13 degrees. This is a critical number to us, 53.13 degrees that I'm going to go and have. This is going to go and tell me that whatever this triangle looks like over here, I'm going to have this 53.13. Well, what kind of triangles could I have inside of here? I could go and have a voltage triangle here, because it's just a series circuit. I can have a power triangle. I can have an impedance triangle. I'm going to move straight to my power, because I'm already given this value over here as well, my Z. And I know that my E squared over R gets me to power. In this case, the power that we would be looking, if we're looking at the total amount of opposition as Z, the power that we would get out of that would be my VA. So we're going to go and convert this thing straight into VA by using 120 squared divided by 20. 120 squared divided by 20 equals a value of 720. So I've now established that this thing is going to be at 720 VA at an angle of 53.13. Is VA a type of power? Absolutely. Can we always add all types of powers together? Absolutely, provided we do so at the proper angle. What is this one at? It's at 53.13. I don't actually need to break it down into the watts and the vars that are going to be on here, because I've already got this thing at an angle, right? We've got theta that has been set out for us. What about this one over here? Do we have power from this one? Not yet. We're going to do that real quickly. We're just going to go and say, look, we take our E squared over top of my R is going to equal my power. Same value of R as what we had for Z, so therefore we're going to go and get the same computation out, 720, but now it's going to be watts because it's over top of this resistor over here. Okay, now what we're going to do is we're just going to do simple vectorial addition. What we're going to do is we're going to go and take our 720 watts at angle 0. We're going to go and add that now to this 720 that we're going to go and have at 53.13 degrees. 53.13, 720. And altogether, we're then going to go and establish a brand new triangle for this entire circuit. And guess what? That's exactly what they're asking us for, right? They want totals from this thing. So let's go and give them that total. We're going to go and take 720, so 720 angle 0 plus 720 angle 53.13 degrees. That's what we had up top over here, right? So we punch all that together, we hit equals, we're already inside of our polar format. When I do so, I see I get a brand new VA out of this thing that is going to go and give me 1287.9. So we're just going to take that word value, we're going to go and put that to 1288 VA, 1288 VA, I should say. That 1288 VA, if we divide our volts out of it, VA divided by volts just leaves the A, leaves the amps. So we can go and figure out what our line current is, but we can also, off of this, remember we just added these together, we can get our degrees, 26.56. So this is 26.56 degrees that we have over here. If we have gone that 26.56 degrees, we just need to take the cosine of that to go and establish our power factor. We will do that. So cosine 26.565 gives me a value for this one of 89.44%. So I've got an 89.44% power factor. Lovely. Okay, now that we've got that total power factor for our circuit over here, what we can do is we can figure out a total line current as well. We're just going to take that 1288, and we're going to divide this thing by 120, our line value of voltage, and we come out to a line current of 10.73 amps that we're going to have. Okay, go back to that drawing that's inside of your binder. All they ask right above it, it says, is calculate the total line current and the power factor for this circuit. We just did that. We went and we took this motor, because we had a power factor for that motor, we could then go and take it at its angle. We just found the total power of that motor and we added it to this power and we created a brand new circuit, brand new triangle, not circuit I should say. And from that triangle we were then able to go and pull out our VA, and from our VA and our triangle we were able to pull out the power factor and our line current from it. This is the simplest method to do this. Go through the next 3 pages in your binder. Just pause the video, calculate through it with the book, take a look at how they're getting through stuff there using different Pythagoras and stuff like that. But just remember that it is able to be shortcutted just by going and adding all these VAs, but you have to do the VAs at their angle. In other words, this 720 had to be at its 53.13. In fact, if you go all the way through this one, and this is a really important, star that I want you to go and note, is that if you go to right above where it starts, example number 8, they've got a paragraph over there that says, and I'm going to quote directly from the binder over here, it says, when using the power triangle method, remember that the apparent power, the VA in one branch, cannot be added directly to the apparent power in another branch unless the branches have the same power factor. I want you to cross that one out, that whole little mini paragraph. We can add VAs, and I want you to go and write, instead of that one, VAs can be added if done at their angle theta, or something like that. Something that's going to go and tell you that, look, I can add VAs together. If I add VAs together, then I'm going to be able to go and create a grand total VA, but I just have to remember to keep these things at their angle theta. What we did over here was pretty straightforward. We jumped through, we found just one simple line that we had off of that. What we're going to get asked to do is just going to get more and more complicated from this point forward. But we don't need to go and overcomplicate it. Once again, what you need to be able to do is solve circuits and describe. And what we're doing right now is we are solving real-world circuits in the way that we would normally go and solve them. Take a look at this one over here. We're on to example number 8. It says we got a 120 volt, 60 hertz system. We got 2 single-phase AC induction motors that are going to be connected in parallel with a resistance heater. Now, anytime that I've got a heater, that's all going to be true watts, 100% power factor. Anytime that I got motors or transformers or generators or ballast, there's going to be some sort of a lagging power factor off of them. What they want us to do is they want us to calculate the overall power factor. And what they're going to do is they're going to go and jump through from component to component to component. And they're going to go and take a look at these as individual little sections. And then they're going to start taking all of these different values, of the different motors. They're going to solve for the watts of the VARs on each one individually, and the watts of the heater, and then they're going to go and add up this watt, and this watt, and this watt, and then this VAR, and this VAR, and they're going to form a brand new triangle that's going to get them all the way out to here. What we're going to do is we're actually just going to go and take this VA, and this VA, and we're going to go and add them all together, and we will get to the exact same triangle, but with far, far fewer steps, because what we're going to do is we're going to go across from here to here, then we'll go to this, so the first one in there, this one, and we're going to end up at the exact same one. I'm not very good at drawing. You've seen that obviously demonstrated numerous times, but we'll see that we're going to end up at something that's going to have the same vars and the same watts. So let's go and do that. It's super simple. I say that right now, maybe it's not super simple. I don't find it to be particularly challenging. I don't know if you are finding it to be incredibly challenging as well, but hopefully, you're starting to get the hang of it. So let's go through this one. Let's start by changing all of these power factors into angles. So we're going to take the inverse cosine. Remember that cos to the -1 of my power factor is going to be equal to my angle. So I'm going to do that. We're going to start with the very first motor. The first motor we see has got a power factor of 80%, so I'm just going to go second inverse cosine of 0.8, which gets me to a degrees of 36.87. So this one over here is going to be 36.87 degrees. This one over here, inverse cosine of 0.6, gets me to a value of 53.13 degrees. I don't know if you've done enough triangles in your practice yet, but you should recognize those as all being components of 3, 4, 5 triangles inside of here. Anyways, we've got these ones now punched in as actual angles. The next thing that we need to do is we need to go and figure out what we have for our total amount of power. Well, we don't have anything inside of here other than we know that they're in parallel, which means that they got 120 volts across every component, and we have got the line current in. Well, line voltage and line current together gives me my VA. So if I take 10 amps multiplied by 120 volts, that's going to go and give me my VA. V times A equals VA. So this one, first one over here, is going to be 1200 VA. 120 times 10. Okay. My next one is going to go and be 6 times 120. If you do 6 times 120, you're going to come out to 720. So it's going to be my 6 amps times 120 volts. My line value is 720 VA. This one over here is going to be 8.3 amps, and it's going to be 1 kilowatts. I don't need to bother trying to go and create any sort of a power because they've already given it to me inside here, but I could just otherwise, if I needed to, do 8.3 times 120, it would give me the same value. This one's going to be 1,000 watts that I'm going to go and have. Is the watts the same as the VA? Absolutely. My VA, it's all resistive. I could go and say that this, instead of just being 1,000 watts, I could write it as being 1,000 VA at angle 0, which is what we're going to do. We're going to put each of these now in at their angles. 1200 at 36.87. So let's start by making sure we're in polar format. I'm going to go and add these in. 1200 angle 36.87 plus, then I'm going to add in my second one, which is going to be 720 angle 53.13 plus, now I'm going to go and add in my heater on the end there, 1,000 angle 0. And when we do that, we punch it in, it comes out to a grand total of 2,720.5. I'm going to write that value in, 2,720.5 as my absolute value that I'm going to go and get out of this thing. And then if I go and use my second function, take this over, it's going to go and give me my phase angle for this, which is going to be 28.4. 28.4 degrees that this thing is going to go and be at. If I have got 28.4 degrees, I can go and convert that into a power factor by taking, the cosine of 28.4. So we're just going to quickly go and do that. That's 28.45, I guess, is what it should be. So we'll take the cosine of 28.45, which gets me to a value of 87.9%. So I've got a power factor, PF, equals 87.9% that I'm going to go and have inside of here. I want you to compare this value that we just calculated, this 2720.5, with what they show over here on the grand total summation. They show that they're getting to 2721, so a small little bit of rounding between theirs and ours. That's going to be shown up there. What we don't have yet is we don't have these vars and these watts, but that's okay because we can just go and do that conversion once again, right? If we go back, I shouldn't have cleared this one so quickly, but if I go back and I put in 2720.5 at an angle of, sorry, what was my angle over here? 28.4. So I'll put that in at 28.4. That's going to store it inside of memory. We'll just do this conversion, and the conversion spits out a value along my x of 2393. If I take a look at their values over here, I see it's 2392. And if I go back to my calculator over here, and if I take a look at my y operator over here, it shows me 1293.9, so 1294. And if I take a look at theirs is 1296. Now, there's small differences between theirs and ours. That's fine. I'm not too concerned about that. Ours are actually going to be way more accurate because we just punch these things in on the angle than what they have theirs. They've also got some rounding errors because they've been taking some cosines and getting some angles as well. So we have got our complete circuit triangle that's going to go and look like this. This is going to be super useful to us in what we're going to start to do next, because the last things that we're going to deal with inside of this whole module is going to be starting to fix my different poor power factors that I might go and have. If I have got poor power factors, I'm going to go and counteract some of my inductive vars by adding in some capacitive vars and vice versa inside of these. So we'll come back to circuits that are going to look very similar to like this. We're going to do that same thing where we're just going to go and find our angle, our angle, our angle. We're going to find our VA, our VA, our VA, and then we're just going to go and add those together, you know, VA at angle theta plus my next VA at angle theta plus my next VA at angle theta, etc., to get to my total out of these circuits. All right, that's example number 8. They've got one more example. They lost the bolding on the title of that one, but you can just find the picture over here. And they give us this very last one here where they're saying there's a watt meter. You can't see it, it's hidden. But there's a watt meter that is reading this circuit as being 600 watts. And they want to know what is going to be my total line currents, so my amps, and they want to know what's my power factor going to go and be for this setup that we have over here. You should notice that this is a series circuit, and this over here is a parallel branch, which means we're a series parallel circuit, which means that we could get tripped up if we use the wrong values. As a result, I'm going to want to take everything to power as quickly as possible. We're going to want to figure out what we've got for our watts. We're going to want to go and figure out what we've got for our vars, and then we can take everything back out of it. Let's start with this one over here. If I go and use my E squared over top of R formula, I would see that I'm placing 120 volts over top of 30 ohms. So we'll do 120 squared divided by 30 ohms of resistance, which gets me to a grand total of 480 watts. So I've got that over there, 480 watts. I know that that 480 watts plus whatever watts I've got coming out of here together is adding up to go and become 600 watts. Therefore, I know that I can go and subtract that out to find the difference over here. 600 minus 480, you should be able to do that one hopefully mentally by now. It's 120 watts that we are going to go and have off of there. So we've got 120 watts that is going to be inside of this circuit. Do we know anything else about that circuit? Not really, other than we know the total impedance. Can I do E squared over top of R? Absolutely, because the impedance is the entire circuit. So if I do E squared divided by 40, that's going to go and give me my VA for that circuit. Let's do that. 20 squared divided by 40 equals a value of 360 VA. So I don't know what exactly is happening inside of this circuit, but I do know that I've got 360 VA and I've got a wattage of 120, and that therefore I should also have a VARS that's going to be out of that one. We don't know what that VARS is yet. Let's go and figure out what that VARS is, and once we have that VARS, then we can just go and add everything all together. We don't need to go through the rest of the steps that they're doing with this RL, XL, etc. We're just going to go and figure this thing directly out as far as my VARs. So if I do 360 squared minus 120 squared, and I take the square root of all of that, Pythagoras, that should give me this far side of the triangle. Square root of 360 squared minus 120 squared, put a bracket around that thing, and we come out to a value of 339.4 vars that we are going to go and have. What type of vars? Well, they're all going to be inductive, so it's 339.4 vars. Is there any other method that I could have used to solve it? Absolutely. I could have just used cosine of these two over here to go and establish a angle, and then use the inverse, or use these to go and establish my power factor. From that, I could also then go and take my cosine, and then I could go and add my VA in. Either method would go and work. If you decide to use these two values together to create an angle, then you're going to have to go and add it in 360 at angle that, plus 480 at angle 0. We're not going to do that on this one because we've already done a bunch like that. We're going to do one where we're just going to go and add in all of our power together. In other words, I'm going to go and take that 480, I'm going to add in $1.20 for my watts, so 480, 120, and then I'm going to go and add in this 339.4 as well, and then we're going to get to our net sum for it. 480 watts, which means they're angle 0, plus 120 watts, angle 0, plus 339.4 at an angle of 90 degrees, which is going to go and give me a grand total of, and right now we're in XY, so it's giving me my X and my Y values. We'll just do a conversion. A grand total of 689.34. So that's going to be my total VA. 689.34 VA that I'm going to go and have. And this is going to be happening at an angle of 29.49, so 29.5 degrees. That we'll have over here. Excellent. Okay, so we've gotten this thing all the way across to my VA. If you go and take a look inside of your book, they do get to the VA. They go about it inside of a different way. They wanted to go and get my total circuit current that I'm going to go and have, plus my power factor. We've got our degrees over here, so we're going to take the cosine of 29.5, and that's going to give us our power factor. Cosine of 29.5 equals 87% power factor. So my power factor is 87%. My amperage is just going to be my VA divided by my volts that I'm going to have. It's going to leave us the A. So we're going to take 689 divided by 120. Gets me to a value of 5.74 amps. 5.74 amperes. Lovely. Okay, that taps us through this entire learning task 8. It's a doozy. You know what else is really a lot of work? The self-test that goes along with this one. Go through the self-test, do the solve, don't just go to the back and say, yeah, that's what I would have written. Because when you do that, you fool yourself that you know what you're doing, and then when it comes time for the exam, I find out differently, and I don't like that. I like it when you do the actual practice until you're competent with it. So do yourself, do me, do the world in general a favor by putting in the hard yards and making sure that you're going through those calculations until you're able to do them competently. Once again, all of the methods that I've shown you inside of here tend to be the simpler and faster methods because that's what I like. I'm fairly simple. I like things to be fast, hence my speed of talking, I guess. But it's not the only way. You go ahead and use any of the methods that are shown inside of these modules as well. They're just as correct. All right, that is it.